Ever wondered if this universe, this reality we're in, could be one among countless others, each playing out every possible outcome of every event? Welcome to the world of quantum mechanics, a realm where the rules of traditional science are turned on their head. Our journey today takes us to a controversial yet fascinating concept known as the many worlds interpretation. This theory challenges our understanding of reality and our place within it. Hold on tight, as we venture into the world of quantum mechanics and the intriguing, controversial idea of parallel universes. Hugh Everett in 1957 proposed a daring interpretation of quantum mechanics, the many worlds interpretation. Picture a quantum event as a fork in the road. In the conventional view, a quantum system takes one path and the others vanish. But according to the many worlds interpretation, each path is taken in a different universe. The universe as we know it is not the only game in town. There are countless other universes, each representing a different outcome of every quantum event that has ever occurred. This interpretation suggests that our universe is constantly branching out into different realities. Every time a quantum measurement is made, the universe splits, creating a separate universe for each possible outcome. This could mean that there is a universe where you aced that test you failed, or another where dinosaurs never went extinct. The many worlds interpretation is a radical departure from other interpretations of quantum mechanics. It eliminates the wavefunction collapse, suggesting that all components of a quantum superposition evolve simultaneously but separately after a quantum event. It reintroduces determinism into quantum mechanics, as the splitting of the universe follows the deterministic Schrödinger equation. In this interpretation, the universe we're in is just one of an almost infinite number of universes, each one a different outcome of a quantum event. If this interpretation holds, then reality is far more complex and fascinating than we could have ever imagined. The many worlds interpretation offers an elegant resolution to some of quantum mechanics' most perplexing paradoxes. Let's talk about how. You see, in the world of quantum mechanics, we often grapple with the measurement problem and the collapse of the wave function. Traditional interpretations like the Copenhagen interpretation suggest a wave function collapse, but the many worlds interpretation sees things differently. In the many worlds interpretation, both the observer and the observed are treated symmetrically. They are both quantum systems, both governed by the Schrödinger equation. This symmetry resolves the quantum measurement problem without the need for wave function collapse. Now, let's delve a little into the deterministic nature of the many worlds interpretation. The apparent randomness that we usually associate with quantum mechanics is actually a result of us witnessing just one of the many possible outcomes in our branch universe. So, the randomness we observe in quantum mechanics is merely a result of us witnessing just one of the many possible outcomes in our branch universe. Despite its appeal, the many worlds interpretation isn't without its critics and challenges. One of the key criticisms is the lack of empirical testability. The different worlds or universes of the many worlds interpretation do not interact, making it incredibly challenging to devise experiments that could potentially confirm the existence of these parallel universes. Furthermore, critics often refer to the many worlds interpretation's implication of a vast, possibly infinite, number of universes as ontologically extravagant or unparsimonious. They argue that this interpretation adds unnecessary complexity to our understanding of reality. Lastly, the many worlds interpretation struggles with explaining the Born rule. This rule gives the probability distribution of measurement outcomes in quantum mechanics. In a deterministic universe, as the many worlds interpretation suggests, explaining this rule in purely deterministic terms without additional postulates becomes a significant challenge. Yet the very challenges that face the many worlds interpretation also make it a fascinating field of research. Today, the many worlds interpretation has a considerable following among physicists and philosophers of physics. This compelling interpretation, although still a subject of intense debate, is captivating the scientific community with its radical, yet simple resolution of quantum measurement problems. Its appeal is not just in its elegance, but also in the profound insight it provides into the fundamental nature of reality. The notion that every quantum event spawns an almost infinite number of parallel universes, each representing a different outcome, challenges our conventional understanding of the universe and its singularity. It paints a picture of a vast multiverse where all conceivable histories and futures exist simultaneously. Despite its criticisms, the many worlds interpretation continues to fuel ongoing research, particularly in the realm of quantum decoherence. By pushing the boundaries of our understanding, it sparks a quest for a more intuitive grasp of quantum mechanics. As we continue to question and explore, who knows what other worlds we might discover in the vast multiverse of quantum mechanics?